So we've got this periodic table on the wall, and it has a very interesting shape. Right? You might expect that, well, why don't we just put it in one giant rectangle? Why does it have all these jigs and jags in it? Well, that is there for a reason. And to understand that, we can go back to 1869. A guy named Dmitri Mendeleev was looking for patterns in properties of elements. And he noticed that certain groups of elements had similar properties. So he found that if he listed the elements in order of increasing mass, those similar properties repeated in a periodic pattern. Periodic means it happens in a repeating pattern. So Mendeleev summarized these observations into a law. It doesn't explain why, but it just says what happens. It's called the periodic law. When the elements are arranged in order of increasing mass, certain sets of properties recur periodically. And we can illustrate that this way. Here we just have the first 20 elements in a line, in a row, 1 through 20. And the colors here are used to indicate atoms that have similar properties. So helium in the green has properties that are similar to neon, and their properties are similar to argon. And these properties recur every 8 elements. It's a little bit like an octave on the piano. You got middle C, and you go up 8 keys, and you got another middle C, and then you got another, and those are harmonics of each other. It's sort of that same idea. So instead of just a long line like that, Mendeleev organized the elements that were known in 1869 into a table. And he arranged the rows so that elements with similar properties fall into the same vertical column. So he took that line of 20 and formed it like this. And so here we have helium, neon, and argon that I mentioned before. Those have similar properties, so they're in the same column. Hydrogen, I think of him as the baby brother of the element family. He breaks all the rules. It's kind of hard to put him in a category. In some ways he belongs over here because he shares some properties with these guys, but in some ways he belongs over there. Some periodic tables will have him in both places. Some will have him in one or the other. It's more common to see him over here. But these elements here in the purple, beryllium, magnesium, calcium, those share similar properties. Mendeleev's table had some gaps in it because not all the elements were discovered yet. all of the naturally occurring elements have now been discovered. The new elements are all man-made and they are not stable. So in those gaps, he predicted that elements would be found. And not only that, he predicted their properties. So there was a gap under silicon, and so he called it ecosilicon, just below silicon, and he predicted that it would be found. And sure enough, that was discovered by Clemens Winkler, who's a German chemist. He named it germanium after his home country. Back in the old days, you discovered an element and you could just give it a name. And some elements had different names, and then people had to get together and decide, okay, we got to have one name for this. Now it's a lot more complicated. This is just for interest. This is a periodic table showing time of discovery. So in the light blue before 1800, in the first half of the 19th century, the dark blue ones, and then the purple ones in the second half of the 19th century, and then in the 20th century, technetium, rhenium, francium, some of these guys down here, and then these are more modern. Now this periodic table just shows up to 2012. These elements here have been synthesized and given names now. I don't remember what they are, but they're there. And this is how, in 1869, Dmitri Mendeleev completed the first periodic table. Tetris, anyone? No? I put that one in there just for my own amusement. Students never laugh. That's okay. So in the modern periodic table, we list the elements in order of increasing atomic number instead of increasing relative mass. We also have more elements because more elements have been discovered since Mendeleev made that table. There are a couple of places on the periodic table where the order of mass and the order of atomic number disagree. We can't really see them on this periodic table, but let's see, where are you? Lead and bismuth. Those guys, lead and bismuth. Lead actually weighs a little more than bismuth does, so that's out of mass order. And there's another one too, another pair. So this periodic table is showing us major divisions. So we've got the metals in the light yellow, we have the nonmetals in the green, and then we have semi-metals. They're also called metalloids or semiconductors. So here we have the metalloids in the purple. So there's this dark line that goes down the periodic table like a set of steps, right? And that's the dividing line between the nonmetals and the metals. The periodic table up here didn't have that line, and so we put it up there with blue tape. Every periodic table that you'll have to look at for an exam will have that line, because it's a very useful line. We should be able to identify, is this element a metal or a nonmetal based on its position in the periodic table. So those three classifications, these are common characteristics of these different types of elements. Metals tend to be good conductors of heat and electricity. They're ductile, meaning they can be drawn into wires. They're shiny, usually. And what's more important for chemical reactions is that they tend to lose electrons. So metals tend to lose electrons when they undergo chemical changes. Nonmetals are not metals. They're kind of opposite. They are poor conductors. They're not ductile. Oh, I skipped this word malleable. Malleable means you can pound it into a sheet. I was watching, my 10-year-old wanted to watch the 3 Iron Man movies over the weekend. So I sat and knitted and watched them with him. And there's Tony Stark, and he's using the malleable property of metal when he's trying to form this helmet, and he heats it up and he's hammering it on the anvil. Metals will do that. You can flatten them and shape them like that. Non-metals are not malleable. They will either just dent. No, they won't dent. I'm sorry, that would be malleable. They will just shatter, typically. Most important, though, is that nonmetals tend to gain electrons. So opposite, metals lose, nonmetals gain electrons. And then we got the guys in the middle, metalloids or semi-metals. Their properties are mixed. They're sort of in between. More information on the periodic table. We have main group elements. That includes these 2 columns and these columns over here. So these are all shown in yellow here. You can also identify them because these parts stick up. So any column that comes up higher than these guys is a main group element. These are called the transition elements because they sort of bridge the gap from this side to that side. This is blue. It kind of looks like this is a river bank, and that's the other bank, and here's a river in the middle. And they are that transition between. We also identify group numbers and periods. So the group number is the number assigned to a particular column in the periodic table. There are 2 different ways of numbering these. So we see 1A, 2A. We also see 1 and 2. And so that doesn't seem very different. It gets different in here, and then over here we see this is like 6A and 16. So the top is what we currently use in the US, and the bottom one is the one that the International Union of Pure and Applied Chemistry Scientists have decided should be used. I'm going to use the one on the top because I think it's easier. We're really never going to refer to the group numbers for the transition metals. We don't get into that in this class. We also have periods. The periods are the rows, and so they're just 1 through 7. Any questions? Some of the groups have special names, so you should know the names of these groups. The noble gases, group 8A, they are mostly unreactive. The alkali metals are those in group 1A, and they're all very reactive. The alkaline earth metals are right next door in group 2. They are fairly reactive, not as much as the alkali metals, and then we have the halogens in group 7A. So each of these groups contains elements with similar properties, and so it's convenient to be able to refer to the group 7 elements as the halogens instead of saying fluorine, chlorine, bromine, and iodine. It's like the boys, right? Well, the boys went off and did this. You don't have to name all of them. We know what you're talking about. So we mentioned that metals tend to lose electrons and nonmetals tend to gain electrons. Well, how many? Main group metals tend to lose electrons to form cations with the same number of electrons as the nearest noble gas. Might not make much sense. We'll look at a periodic table. Main group nonmetals tend to gain electrons to form an anion with the same number of electrons as the nearest noble gas. I'll come back to those, but this is what that's talking about. So let's talk about the metals first. So here we have sodium. Sodium is element 11 on the periodic table. So how many protons and electrons does it have? It would have 11 protons and 11 electrons. So when it loses an electron, so it had 11 protons, 11 electrons, we don't care about the neutrons right now. If it loses an electron, then how many does it have? 10 electrons. What neutral element has 10 electrons? Neon. Neon is element number 10. This is really, I should make a different periodic table to illustrate this. There's neon. All of these metals over here are going to lose 1 electron, because in losing 1 electron, they have the same number of electrons as the nearest noble gas. You might say, well, that's all the way across the periodic table. This should probably be more like a cylinder, right? But that doesn't fit well in people's pockets or anything, or on the wall. So it's flattened, a little bit like a map of the Earth, right? We see lots of flat maps of the Earth. Is the Earth flat? No, it's a sphere. We have globes, but those are awkward, right? So think of this as being a flat map of a cylindrical thing. And so sodium is just 1 square over from neon. Potassium loses 1 electron, and it'll have the same number of electrons as the nearest noble gas. So here's magnesium, element number 12. 12 protons, 12 electrons. If it loses 2 electrons, then it'll have 10 electrons. Same as neon. What about the nonmetals? Well, here's fluorine. Fluorine is element number 9. Fluorine has 9 protons and how many electrons? Neutral atom. 9. So if it gains 1 electron, then it has 10 electrons. That's the same number that sodium and magnesium got. they had to lose electrons. Fluorine has to gain electrons. Oxygen has to gain 2 electrons. Nitrogen has to gain 3 electrons. When it gains 3 electrons, it has a 3 negative charge. Any questions? Well, let's go back to those slides I skipped. So in general, the alkali metals, group 1, have a tendency to lose 1 electron, form +1. So group 1, +1. The group 2, the alkaline earth metals, +2. The halogens tend to gain 1 electron and form -1 electrons. The oxygen family tends to gain 2 electrons. So this is a helpful guideline here. For main group elements that form cations with predictable charges, the charge is equal to the group number. And that's why I like the 1A, 2A, 3A group numbers. For the anions, the charge equals the group number -8. I'll show you another way to remember that as well. The transition elements are squirrely. They can do different things. So let's go back to this periodic table now. Group 1A, they form +1 ions. Group 2A, +2 ions. There's aluminum over here in group 3A, +3 ion. These are transition metals. They don't always follow that pattern. In fact, they usually do not, and so we can't use that. We're talking about main group elements. These are the halogens. They all form -1 ions. Oxygen family is -2, nitrogen's -3. So oxygen, its group number is 6. If you subtract 8, you get -2. So that's where the group number -8 thing comes in. I think it's easier, less math. Anytime negatives are involved, people kind of lose their minds. If we think of this as a board game, like a really dorky, maybe not so fun board game, but we're going to start over here. You start at like if I want to know what the charge on nitrogen is, I go to the end of the row, and that's my starting point, the nearest noble gas. That's going to be 0, and I count backwards. So 0, -1, -2, -3. So selenium here, I start over here, -1, -2. I think that's easier than group number -8. So we should be able to predict charges for main group elements. So nitrogen, it's up here. Is it going to be positive or negative? Negative. Non-metals form negative ions. So how many negative? 3. This will be 0, -1, -2, -3. So the charge will be -3. When we write the symbol for that ion, we use the element symbol, and then we indicate the charge as a superscript. We don't want that superscript to be mistaken for an exponent. So instead of saying -3, we say it's 3-. How about rubidium? +1. It's down here in group 1. Group 1 elements form +1 ions. So its charge is going to be +1. And when we write the symbol for that, we've got rubidium, and we just put a plus up there. We'll find that chemists often don't write the number 1. We understand it's there, so we leave it off. Any questions?